Hello students, last video we have discussed about regular expression and its properties, and if you are saying that something is a regular expression, then every regular expression can be converted to finite data meta, and every finite data meta can be converted to regular expression. So those two conversions we'll discuss in this video. So first one, as I told you, the power of both the things are same, regular expressions and finite data meta. But there is no relationship like there are few languages which are represented by RE but not by finite data meta. There is no such concept. If something is accepted by the regular expression, definitely it must be accepted by the finite data meta. If you can't, then you can convert from RE to FA. If something is accepted by the finite data meta, definitely you could able to write the regular expression. If you can't, then you convert this finite data meta regular expression. If someone expecting such, regular expressions are finite data meta. Okay. So then the most restricted here is DFA, but the conversion of regular expressions and NFA both are same. Like what is required to us that we are going to specify. Like you take the third symbol from the left hand side is B. In NFA you have written like this, right? So first is ARB, second is ARB, third one is A, followed by anything with the A comma B, right? Then you can write the regular expression ARB, ARB, A, anything with the A comma B means the universal language. That's it. So this is how it is going to write the regular expression. How simple as NFA. But when it comes to DFA, the problem starts because it's the most restrictive type. Okay. So then how we have to convert it? See, regular expressions means we are going to have the symbols first of all. If it is epsilon, what should I do? So simply you take from a start state to another state, you take the A. That's it. No need to do anything. Okay. Epsilon, take the epsilon instead of E. Empty, no movement because there is no transition. Okay. So whenever you're asked to convert into the regular expression to finite data meta, make sure that there should be only one starting state and take only one final state, and whatever the expression you want to write, you write in the middle, right? Then let me go with the union. For example, we are having two expressions, R1 and R2. Like you are having your A star and B star. Assume that. How to perform the union of this? Just introduce a starting state and a final state. Okay, and make the epsilons one state. So from this source to the destination, either you can take A star or B star union, even or E2. This is union. Go for concatenation. How we can do it? E1 and E2. E1 and E2. So you have to just make a note edge from E1 to E2 epsilons. Okay, simple as clean closure. For example, E, how many times I should take? Infinite number of times. So you can take like this. Right. Let me go with this. E, how many times I should take? Any number of times. Then you can take the self loop. But sometimes you have to take 0 times also, right? You can take like this. Sometimes you are supposed to take 0 times. Then from starting state to final state, you take directly epsilon. Either you take 0, clean closure means what? Star. Star means what? 0 to infinite. So from the starting state to final state, either you take 0 times, or you take 1 time, or you can take 2 times, 3 times, 4 times, 5 times. That's what the automata is. Okay, you got the same, right? You can remove the ink on it. So this is how we are going to. Then how we have to convert this regular expression to finite automata. Sorry, we are doing what? Regular expression to finite automata. An example. Okay, don't forget about the right heading. So what is the first and the foremost step in the conversion? should keep, as we have discussed in the earlier. First, you have to keep the starting state and final state. Then you can go for it. Same way how we are doing it. With the example, let me explain. Sorry for this. Okay, let me go with this. There we should have. There it is. Okay, yeah. So keep this in a starting state and final state. QS, right? And QF. So this is what regular expression to finite data method. So just keep the regular expression like this: a plus b whole star a plus bab whole star. Okay. So logic is very simple, guys. Always you should go for the least precedency operator first. So what is the least precedency operator here? Plus. So how can you remove the plus? Just by introducing the two edges. Okay, what we have to do? We have to introduce the two edges for that. Then how it is going to be happen here? So QS, then you can take a plus b whole star a to the same state. You can take b a b star. Okay. So what is the least presence operator here? Plus. And what is the least presence operator here? Dot, dot, and dot. It's very simple, guys. The concatenation. How can we do it? The concatenation we have already discussed, right? So I'll tell you in another way how to do the same concatenation in a simple way. So whenever it is in a union operator, introduce the parallel edges. Plus means introduce parallel edges. That's what we have done earlier also, but we have discussed with some diagram. Concatenation, introduce a new state. Okay. Star, introduce a new loop. Then always you follow the lower to higher precedency. First do the lower, then go for the higher. So now here the least precedency operator out of plus, star, and dot is dot, because plus is in parenthesis, and here dot. So in place of the dot, just introduce a new state, guys. Means it would be like this. From the starting state, you're having here a plus b whole star. In place of dot, you take the big dot and a. That's it. Just increase the size of the dot and increase the size of these two dots. You're going to get b and a and b star. That's it. It's very simple. Then how to remove the star, right? So clean closure, that's what we have discussed earlier, how to do it. So just take the same automata as it is, QS, okay, B, A, then the final state. In between this, simply introduce a new state by saying B star. So epsilon, epsilon, that's it. B star self loop. If you want no B, take epsilons, 1B take it, 2B's like that. Same way, A plus B whole star, just introduce a new state by taking the loop of A or B, then epsilon. Earlier what we are having A. So this is how we have to convert a finite regular expression to finite automata. This is called state decomposition method. We are creating the new states or state creation method. This is how it is. Simple logic. If it is a union, introduce a parallel edges. If it is a concatenation, introduce a state year, year, and year. If it is a star, introduce a state by taking the loop. new loop and new state, both you have to mention. Then take this thing, that's it, nothing more than that. You try with another. Then we can even convert a finite determinator to regular expression. The thing is finite determinator to regular expression, just titles were reversed. So same guys, first you have to mention that there should be only one starting state and one final state. If you don't have, or if you have two final states or two non-final states, you add it, otherwise you don't need to do these two steps. And if there are parallel edges, remove the parallel edges. For example, if I'm having like this A to B, if I'm having R1 and R2, then remove this by introducing the R operator like R1 plus R2. Reverse the process what we have done earlier for this, right? Okay. Same way, if you're having sequential edges like R1 and R2, remove the state by performing the can. Just decrease the size of this state to dot. You are going to have R1 dot R2. Self loop. If you are having a self loop R1, then reduce it to R1 star. Then let me explain with an example. Okay, first go for the parallel edges if you have. Otherwise, just go with the sequential. See, the Q1 is having one state incoming and one outgoing. You can reduce it to dot. In Q2, one incoming, one outgoing. You can reduce it to dot. But Q3, one incoming, two incoming, two outgoing. Don't do such a. First go for one incoming, one outgoing. So you can write it Q naught to 1.0 QF. In place of state, just decrease the size. Then same way you can take it Q3. What we can write here 0 and 1.1. You can write here 1.1. Then you can go for the 1. We have just reduced these two. Now we have parallel edges. Remove it by introducing R. So you can write it Q naught 10 QF, and from Q naught you can take Q3. Reduce the parallel edges by adding 0 or 1 1. Keep it in the brackets and 0. Sorry, 1. Now again, one incoming, one outgoing. You can reduce this state like this. Q naught. So from Q naught to QF, you are already having 1 0. Now you can reduce this as we are having one incoming and one outgoing. Then you can write 0 plus 1 1 dot 1. A state can be removed if it is having only one incoming and one outgoing. If not, try with the self loops and all. Now Q0 to QF we are having parallel edges. We know how to remove the parallel edges by introducing OR operator. Okay. Then you can write here Q0 to QF. Okay. Then you will be having 1 0 R 0 plus 1 1 dot 1. Right. So, but here we have not considered the self loop. Okay, you can do it, no problem now. See, here we are having the 0. Here we are having the 0, not changed here. Now, whenever you are removing the Q3, we are having a self loop, right? How to remove the self loop? By just writing the 0 star 1. I'm going to say that 0 plus 1 1, 0 star 1. So same thing you can write here, 0 plus 1 1, 0 star 1. So I just explained without confusing you with the self loops earlier. So I did it. Then we can go for the star. Simply you add it, nothing more than that. So this is the regular expression for this finite automata. If you want, you can try it with the another examples. So definitely you'll get the same output. Of course, not same. You may get the different output, but the same automata. Okay, the language must be same. So in the next video, we'll discuss about the applications of finite automata and some closure properties of regular sets.